Hey, hello everybody. We start the lecture number 14. And today we are going to discuss the topological time crystals. And topological system, and what we will be interested in the examples of topological insulators. And this kind of systems are solid state systems, which are insulator in the interior, in the bulk, but they are characterized by the global topological invariants. And these topological invariants are robust and difficult to change unless we break the symmetry of the system, or the perturbation is so strong that the gap between the energy bands is closed. And there is one important property of the topological insulators, and this is called the bulk edge correspondence. And if you have a topologically non-trivial system, then if we consider the finite system, then with some edge, then it turns out that on the edge there is something must happen, because on one side you have, for example, vacuum, which is topologically trivial. On the other side we have a topologically non-trivial system, and then it turns out that there are so-called edge states, the states which are localized on the edge, with energies located in the energy gap between the bands, and they are very important because they are responsible for the quantized Hall conductivity in the integer quantum Hall effect. But we will consider a simpler system. Actually, the one of the simplest example of the topological problem. And again, we start with something which we call reminder. And this will be the so-called Schrieffer figure, in short SSH model. And this model was introduced by these persons in order to describe electrical conductivity of a polymer chain. Actually, this two names out of these three names got Nobel Prize for something, for BCS and for research on conductivity of polymers. The system is very simple, because what we have 1D lattice. And of course, we can consider non-interacting fermions in order to discuss insulator, but non-interacting fermions actually means that this is a single, it reduces to the single particle problem. So here we have 1D lattice and a single particle. And the wave function of this particle, of this system, can be written in the basis where this state is localized in the I side of the lattice. It's just as usual. And then what we get simply the tight bonding model. So the energy of the particle can be written as the sum of the tunneling terms, tunneling, hopping between neighboring sites. And that's the standard system which we have considered during this lecture many times. However, in our case, now what we consider, we consider a lattice which have so-called staggered tunneling amplitude. So there is a tunneling between the tunneling changes from one pair to the other. So we can introduce that there is a two values of the tunneling, J and J prime. No. And so on. So actually that means that our crystalline structure is a crystalline structure with a 2-point basis, and we expect two bands in the energy for the eigen values of the Hamiltonian. So the easiest way to obtain the eigenvalues of this for the eigenenergies for the particle is to switch to the Fourier basis, because also we have 2-point basis, but the system is translationally invalid. So switching to the Fourier basis means that we have even and at all odd sides, and the pairs of this vector can be represented in the Fourier basis as the following, by means of the following expression. So when we introduce this expansion, then it turns out that the system Hamiltonian can be divided into independent two-dimensional blocks, which are parameterized by the K quantity, which is simply the quasi-momentum, and as I told you, this reduces to the just 2x2 matrices blocks. This is prime. Actually, if we introduce the basis corresponding to the Pauli matrices, then this matrix can be written in the form that there is a component, so to say, along the sigma X matrix, and there is also Y component, sigma Y matrix. And that quantities is just J plus. Okay, so that's this. And of course, there is no problem to diagonalize this Hamiltonian. So then what we get the pairs, the eigenvalues, plus minus 1/2, and the modulus of J plus J prime. So one comment, we have the pairs of, actually our energy spectrum is symmetric with respect to zero eigen energy, and that comes from the so-called chiral symmetry. Because our Hamiltonian fulfills the following relation. And then what it means that if we have a certain eigenvalue in a certain eigenstate, then of course we can multiply this by minus, and then that from the Kähler symmetry, it means that this is sigma z h sigma z, and from this what we get multiplying by this equation from the left by sigma z matrix, we get sigma z So that means once we have a eigenstate corresponding to the energy E, then we can construct another eigenstate corresponding to energy minus. Okay, this is one thing, but another one, that this system, we can define a topological invariant, a Wanding number. This Wanding number will denote by nu. And this winding number is simply it tells tell us how many times the endpoint of the vector x k h y k, how many times this vector encircle the origin of the coordinate when we go through the Brillouin zone. And it's better, of course, to illustrate with the, but I need this one. Illustrate this with some plot. Okay. So there are just two important cases. The first case, assume that J prime is larger than J. This is the case that when J prime is smaller than J, that of course this is equality. So what happens? Suppose that we have chosen the parameters of our lattice where J prime is larger than J. So then, of course, we know how the energy eigenvalues. What are the energy eigenvalues? They form two bands, and this is just the energy versus quasi-momentum. And then we can analyze what happened with our vector, whose components are h, x, and hy, when we change k over the Brillouin zone. So in this case, it happens that it encircles the origin. So it means that here we have the winding number equal 1. Then there's another situation where the relation of these parameters is changed, and then it happens that we again have the two bands, but this times our winding number is equal 0. So you see that between these two cases, there's the parameter, integer parameter, can change only if the gap between the two energy levels is close, and that is happening when J is equal J prime. And of course, when we look at the infinite lattice, then the choice which is J and which is J prime is somehow arbitrary. So what is important? The important is a change of this topological invariant and not exactly the number itself. Nevertheless, we will see in a moment that that when we consider the finite system, in this case, we will deal with the topologically non-trivial situation, while in this case, it is just a trivial one. Okay, so how to do it? Just let us consider finite system, finite lattice. Again, it's better if I use some plot. Okay, so we have two situations. In the first case, we have J prime equals 0, so on. So that means that this is a situation when we have simply j prime smaller than j. And that corresponds to the last column. And we are saying that this is topologically trivial situation. And, however, this is just, of course, very extremal case, but it is very helpful to realize that when we change the relation between the tunneling amplitudes and we switch to this one where we have j equal 0, that is the other one, which corresponds to the first column, and we are saying that it is topologically non-trivial. And indeed, because now what is different? In the bulk, in the interior, we have we expect similar states like in the first case. So basically on the edge and in the bulk, we have the same kind of states. But now the situation is different on the edges, because from this plot, we know that apart from the states which are localized in this pairs of sites, there must be also two states which are purely localized on the edge. And this is topologically non-trivial. And of course, that is these two extremal cases are very simple, but what is interesting and not trivial is the fact that turns out that even if j is not equal 0, but j prime is larger than j, there are still edge states. There are states which are localized on one edge on the other one. But of course, the localization lengths, how deeply they penetrate the interior, it depends on the relation between these two tunnelings. And it means that the localization lengths of the edge states is given by 1 over the logarithm of the ratio of these two tunneling amplitudes. And this is an example, a simple example of the so-called bulk edge correspondence. When we have topologically non-trivial case, then when we consider finite system, we expect the presence of edge states. Okay, so that's the introduction. And now we can switch to topological time crystalline structure. And of course, let us consider a simple example. And as usually we do, we consider a particle, for example, atom bouncing on bouncing resonantly on an oscillating mirror. So then in the frames of that, this is just our system. Usually there is a mirror which is oscillating. There is a particle which is bouncing resonantly. And now and again we switch to the frame oscillating with the mirror. Then the mirror is fixed, but what changes it in time is just the gravitational acceleration. But now we assume that we drive the mirror in such a way that it oscillates with two frequencies, with the frequency omega and with the frequency omega over 2, with some different amplitudes. So then what we do as usually, we consider S21 resonance. We switch to the action angle variables. We switch to the moving frame. And we average over time. And we end up with the effective Hamiltonian in this moving frame, which is a particle with some effective mass. And the effective potential this particle experiences in the moving frame is has two contributions. There is a periodic potential of theta tilde, and plus there is another potential, but with longer, so to say, wavelengths. Because this is theta tilde over 2. So when we plot the effective potential, what we get, this is versus theta. What we get the structure that have a series of double wells. Yeah, this is simply the crystalline structure with the 2-point basis. Then another next approximation, to simplify the description, we switch to the time binding approximation. And that means that we have the energy of our particle bouncing on the mirror takes the form actually of the SSH model, because we have two tunnelings. We have tunnelings between the over the or through the barrier, which through such barrier or through the higher barrier. So that is why we deal with the so-called staggered tunneling amplitudes. And of course, this amplitude corresponds to the localized wave packet, which is moving along S21 resonant orbit with the period S time longer than the driving period. But now what we can do in our system, we can actually control the ratio of these two tunnelings. Because when we change, what we can do, we can change the amplitude, for example, the lambda 1, and changing the amplitude, lambda 1, we change the relation between V1 and V0. So that means that we can change lambda 1 over lambda. This is proportional to this ratio V1 over V0, and from that we have control J prime over J in the SSH model. This is simply SSH model. Okay, so that is one thing. And so the way, let's say, the state, eigenstate of this system, of this particle, can be written as a superposition of S localized wave packet. And of course, in our case, what we have periodic boundary conditions. Now the question is, in order to see the edge states and to really observe this topological character, what we need to create the edge in this effective potential. And how to do it? Because we're, let's say, resonant driving of the system allows us for very flexible manipulation of the system. So in order to realize the edge, what we have to do, we have to add additional perturbation. And this additional perturbation means that there is some additional driving of this system. And this f of t fulfills periodic boundary condition in our crystalline structure in time. And of course, that can be expanded in the Fourier series. And now the key point is to choose the Fourier coefficient of this additional driving so that the resulting additional contribution to the effective potential corresponds to the potential which is a barrier. So what it means? It means that we have a periodic boundary conditions. That means that as a function of theta tilde in this moving frame, without this additional perturbations, that we deal with the periodic boundary conditions. But now, proper choice of this Fourier component allows us to create additional potential, which, for example, has the form of a barrier at some theta tilde. And then when we have a barrier which is sufficiently high, then effectively what we have done, we have introduced an edge in the system. And then we can expect that there are states which are localized close to on one side of this barrier, on one edge, and on the other one. Okay, now how to just and what is the final result? This is an example of the eigenstates of this effective Hamiltonian, and actually these are example of the exact Floquet states of the system. But in the left panel, we can see what is happening in the laboratory frame versus time. That means that, okay, let's come back to our particle bouncing on the mirror. That means that we have detector located at some point close to the resonant orbit, and then this detector, how the probability of the clicking of the detector changes in time. Of course, it depends on what state, in which state we have prepared our particle. If the particle is prepared in the eigenstate of this SSH model corresponding to the so-called bulk state, then we observe that there is just the probability of clicking of the detector is extended along this entire resonant orbit. However, if we prepare the particle in the edge state, and when the edge actually in time is passing close to the detector, close to this edge, we observe the edge state. And there are actually, of course, two edge states. So this is, of course, where in the laboratory frame versus time for fixed position. And just also on the left, right panel, you can see how these states look like for the fixed moment of time, but versus the position in the laboratory frame. So you can observe two edge states, and the bulk state is delocalized along the entire orbit. And actually, this is quite I have shown you the example for ultra cold atoms bouncing on the mirror, but this is pretty general phenomenon, and you can realize in many different systems, provided that you start with the particle which is resonantly driven, and if it is properly driven, then we can observe this topological behavior. And actually, this topological behavior corresponds to some one of the simplest example of the insulator state, which is an example of the solid state system. But it turns out that what you can do, you can take, for example, hydrogen atom, and you can properly drive the highly excited electron by microwave field. And this single electron in a hydrogen atom can behave like a solid state system and can reveal topological properties. And that was, and moreover, even what you can do, if you have two atoms and you drive properly the interaction strength between two atoms, or if you have ultra cold atom, then it is possible because contact interactions is determined by the S-wave scattering lengths, which can be manipulated in the experiment, and then you can create. You can also realize the edge state for this pair of atoms, and this edge state for this pair of atoms is actually a molecule. So the topological properties allows you to create we can call topological molecules, and that was done in the publication by Ali Imani Kopaei and Shudong Tian. That was at all, and this was PRA. Okay, but this is that one. So I have described more in more detail a few examples of the condensed matter phases in time crystalline structure, but we can do more, and that is why now I would like to list some gallery of condensed matter behavior in time crystalline structure. So that would be, let's say, shorter description of the system, but I would like to show you that we can do quite a lot in the time domain. So that is something which is we will call gallery. Condmat in time crystalline structure. So so far I have presented single particle problems, but now let me show you that we can also consider many-body condensed matter phases. Many-body phases. And again, let us stick to the example of atoms bouncing on an oscillating mirror, but now we consider not a single atom, but many atoms, which can also interact. So many bosonic atoms and so we know that, and of course we consider S2-1 resonance, and we know that now this system can be described, of course, by for a single particle. This system can be described by the time-binding model when we know how to do it because I have described this many times. But to switch from the single particle to many particle, what we have to, in practice or technically, what we have to do, we have to substitute these C numbers by operators. And this is, we have, I told you how to, I introduced a second quantization formalism. So you can look at the lecture number 1, or also the some comment observation in lecture number 6. And then in order to switch from between the many body case and single particle case, technically we do the following. We substitute C number by the annihilation operator A. And then we switch from the single particle energy to the effective Floquet Hamiltonian, where we have the part corresponding to the tunneling, which is a kinetic energy part. But now we have the operators, because when we annihilate a boson at site I, we can create in the neighboring site. But additionally now, because for ultra-cold atoms, we know that the interactions between ultra-cold atoms are contact interactions. So there are now additional contribution to this Hamiltonian, which describe which results from the contact interaction between atoms. Where this U okay, this is just Kronecker delta. This is just integral over the period of the orbit, integral of the space for our ultra-cold atom bouncing on the mirror. There is a strength of the contact interaction, which is proportional to the S-wave scattering length, and there is also the densities corresponding to the state localized in the I site, which is the wave packet, which we denoted by the index I, and the interaction it can particles which are prepared in this wave packet can interact with in general with the atoms prepared in another wave packet, and that leads to the effective strength of the interaction in our this is actually Bose-Hubbard Hamiltonian. So, but that means that now can do many different things concerning many body phases known in the solid state physics. So let me give you a few examples. First example will be Mott insulator phase in the time crystalline structure. Okay, usually when we have ultra cold atom bouncing on the mirror, usually we have the situation, okay, this is important, usually the interactions between atoms which occupy the same localized wave packet are much stronger than the interaction between atoms which occupy different wave packets. And this is quite obvious because when we look at this interaction strengths, then when I is equal J, then this expression doesn't vanish at any time, any point in time, and which is in contrast when we have different wave packets, because only the interaction is present when these two wave packets overlap, but they overlap only for a short period of time. Okay, this is the first observation. The second observation, okay, this is observation, but now, and so that means that we can let's restrict to the effective Hamiltonian, which described the bosons on a lattice, but only with the so-called on-site interactions that I have defined. This is as a single U parameter, and then we have only on-site interactions. And now consider repulsive interaction. Which means that our U is non-negative. Usually, of course, we have considered this kind of this similar system when we discussed spontaneous formation of discrete time crystal, but then usually we consider attractive interactions. But what happens for repulsive interactions then? For U times number of bosons going to 0, which means that we actually consider nearly non-interacting system. The ground state of this effective Hamiltonian is a Bose-Einstein condensate. Bose-Einstein condensate, where all bosons are prepared in the same single particle state, which is in the first quantization formalism. It is just the many-body wave function is simply the product of the single particle wave function, and the single particle wave function is a superposition of all this localized wave packet. Just a very simple solution. Now the second limit is more interesting, where we have the interactions which are stronger as compared to the tunneling amplitudes, then the ground state of the system is the so-called Mott insulator state. And this is a good moment for the break, so I will finish after the break. Okay, we're back. Mott insulator state. And this is so how the ground state looks like when you have a strong repulsive interactions. Then it turns out that the ground state in the limit of strong interaction is a single so-called Fock state when we have a well-defined number of bosons in each localized wave packet. So what it means? It means that there is no, if we have a well-defined number of atoms in certain states, there is no phase relation between them. So the coherence between bosons occupying different sides of different wave packets is lost. And this is one property. The second property is that transport of bosons between lattice sites, between these wave packets, is not for free. It costs the energy, and the energy is related to the interaction strength. Moreover, the system is also incompressible. It can be defined quantitatively, but just I'm not going to do it. But so those are a few properties which make this in this phase different from the superfluid phase, and these two phases are divided by the quantum phase transition. And just again, let me illustrate the state by comparing what is happening in this standard situation in the time-independent system of solid-state system. If we have a one-dimensional crystalline structure, so the Mott insulator phase means that in each lattice side we have a well-defined number of atoms. There is no coherence between these atoms. And again, switching from the space crystal to time crystal, we exchange the roles of time and space. Now we fix the position in space. Well, we locate the detector close to the resonantly bouncing ultra-cold atoms. And then the detector says that well-defined number of bosons are coming close to the detector, like on a conveyor belt or some machine gun. So that's Mott insulator in the time crystalline structure. Next example. Next example is somehow obvious because we can consider many body localization induced by temporal disorder. Again, when we have atom bouncing on the mirror, and when we add additional driving to the mirror, which makes some fluctuation of the mirror motion, when we have additional perturbation in our additional terms in our effective Hamiltonian, and these additional terms bring the disorder to the system. And when we have disorder and interactions, then we can realize many-body localization. So this, when we drive in a proper way, which means that the mirror fluctuates, then this on-site energies becomes random numbers. Many-body localization. Next example. engineering of long-range interactions. Of course, it is again in time crystalline structure. And so let me go back to the general effective Hamiltonian, and let us again consider ultra-cold atoms bouncing on a oscillating mirror. So generally, the effective Hamiltonian is like this, and we have interactions coefficient, which the strength of the interactions depends what which interactions between particles in which localized wave packet we consider. And as I told you, usually we can forget about the long-range interaction in this effective lattice because on-site interactions dominates over the longer range interactions. But when we look at the expression for this, maybe let me copy it. When we look at the expression for of this in interaction strengths, so then uh, uh, what we can additionally do, we can modulate the contact interaction strength between ultra-cold atoms in time. So that means that now we can make this coefficient time dependent, and we can change it periodically in time. And why it is useful? Then suppose that we have our windy space. The mirror is located at z equals 0. And suppose that we consider the atoms which are in the wave packet Wi, and the second wave packet which is in the the second atom which is in the wave packet Wj. So this two wave packet are moving along the resonant orbit. At some point, this two wave packet will overlap. And at the moment they overlap, what we can do, we can increase the interaction strength significantly. And of course, we can make the interaction strength in all other time moments small. So that means that the long-range interaction between any wave packet Wi and wave packet Wj, which corresponds to the long-range interactions in this our lattice, can be as strong, in principle, as strong as we wish. And that means that we can engineer long-range interaction in our effective Hamiltonian. And of course, usually when we consider the system time-independent system in some special system, some optical lattice for ultra-cold atoms in optical lattice, the manipulation on the long-range interactions is not possible. But this resonantly driven system gives us another opportunity to control interactions and to do things which are not easily attainable in other situations. Next example. Next example, of course, we know that time is a single degree of freedom, and it is hard to imagine multidimensional time crystalline structure, but somehow we can do it. So this is the next example. It is time. with properties of two-dimensional or even three-dimensional space crystals. So again, I would like to show you some picture. So suppose that we have not a single mirror in one-dimensional situation, but suppose that we have two orthogonal mirrors and atoms are bouncing resonantly between these two mirrors. And if we consider a single particle problem, then the system is simple because it is separable. The motion along one direction is independent on the motion of the other direction. So it is very easy to construct the crystalline structure and the effective Hamiltonian. And the effective Hamiltonian in this case, when you have, for example, S to1 resonant condition for one mirror and for the second mirror, has the form that two-dimensional Bose-Hubbard Hamiltonian. That symbol denotes the summation over only nearest neighbor tunneling between our lattice sides. So this is just let me finish. Where this I course this is just a two index vector with the two indices, and the state corresponding to each of these operator is a two-dimensional wave packet. It depends on x and y. And because when we construct the basis, we know that the single particle problem is separable. So this is simply the product of the one-dimensional wave packets along x and y direction. Okay, so now how I need another picture. And here you can see an example of the state of the system. And this is the lattice which is formed by the ultra-cold atoms occupying localized wave packet which are moving along the resonant orbits. And this plot is for a fixed moment of time. Okay, and now how to see that somehow corresponds to the time crystalline structure which have some properties of higher dimension than one. We know that switching from the space to time crystals, we have to fix the position in space. So we have to locate detector close to resonant orbit. And now we can locate detector at different position. And if we do it, what we can observe. So let me analyze this with a simple state. Suppose that we have a state in this crystalline structure, and it is easier to demonstrate the properties of this system when we consider action angle variables. When we are in the moving frame, suppose that we have the reduced single particle probability density in the moving frame in the angle coordinate representation. And if we can choose any state, but just it is simple, easier to write down just the single particle state when we have a mod insulator state. This is just for example. Because then the single particle reduced probability density in our two-dimensional space spanned by these angles are the sum of the probabilities related to the localized wave packets. When we return to the laboratory frame, then we have the same, but our wave packets depends on the angle in the laboratory frame, and now it also depends on time. And what we do, we assume that we locate a detector at a certain position in the laboratory frame. So that means that we assume that this is constant. And we are asking what happens with the probability of clicking of the detector. So let us plot the space spanned by theta tilde. This is just in the crystalline structure in the moving frame. And suppose that we have 5-to-1 resonant conditions with respect to each of these two mirrors. So that means that we have the lattice, which is 5 by 5. Sorry, it is better, but I have an example for 5-to-1. I have better to write all of them. Okay, so what we have in this space, we have theta y tilde. When we express this with the help of the coordinate in the laboratory frame. But now what we can do, we can eliminate time because we know that it goes linearly. Eliminate and express time with the help of the constant value of the theta in the laboratory frame, and of course the entire expression is equal to theta tilde. Okay, altogether it is simple, but then that can be written in the following way. Okay, and now what we know that this quantity, this one is fixed because we fix the position in the laboratory frame. So that is. And when we change, when we ask what happens when time is going on, that means that we ask it is the same question that corresponds what is theta tilde changing linearly. But that expression is just linear function. So that means that we have, okay, let me see. Suppose that we have chosen this constant equals 0. We have chosen this constant equals 0, then we have actually the cut along this lattice. And that corresponds to this expression, which tells us how the probability of clicking of the detector changes in time. But now we can choose another location, and another location is presented here. That means that we simply choose different value of theta y minus theta x. And in this case, we go along this direction with periodic boundary condition, so that goes like this. And this is presented in that panel. So different location of the detector allows us to observe different cuts of our two-dimensional crystalline structure, but versus time. That is the idea. And the last example is we know that we have time crystalline structure, but now the question is, can we combine time and space crystalline structure together? And we can. This is time, space, crystal. We did it together with Schlabis co-workers. That was so the idea is the following. Let's consider, for example, optical lattice potential for atoms. We have some periodic potential along X, and we assume that this potential is shaken periodically. And we assume also this potential is shaken resonantly, which means that if we have a particle in this classical particle in this potential, then it performs resonant motion. In each potential, we can have particle, and that is just resonant driving. Now, for simplicity, let us assume that we have a simple, we have S1 resonance. Assume that S is equal to 3. So then what we get? Let me describe this. Okay, this is an example that we have here. It is this is a plot versus X, and this is a single side of the potential. This is the next side of the potential, and the next one, and so on. In each side of the potential, if we have a 3-to-1 resonant driving, then we can create 3 resonant wave packets which are moving periodically along the resonant orbit. And now what we can map this system to the two-dimensional time crystalline structure, which means that, for example, we have a certain, let's say that it is this is a first site in space, that one, and the first site in time. Another wave packet will be the first site in space, the second site in time, and so on. So in this way, you can obtain the two-dimensional crystalline structure when we have a temporal index and we have a spatial index. But that this idea can be generalized to the three-dimensional optical lattice, which is resonantly shaken. And when we have three-dimensional lattice potential, which is separable, then the shaking along each orthogonal direction is independent, and the resonant wave packet in this case can be constructed as a product, the one-dimensional wave packets. And altogether, we have 6 indices. 6 indices corresponding to the choice of the site in space, and 3 indices corresponding to the different choice of in the temporal direction. So that means that allows us to create 6-dimensional lattice. And for example, one can analyze 6-dimensional quantum Hall effects or something else. That's all concerning the gallery of condensed matter system. And now, I wanted to show you that time domain is quite flexible for the realization of different condensed matter-like phenomena. And we have the flexibility to do condensed matter in the time domain, then maybe the next step is something what we call timetronics. Which is an investigation and analysis of some systems which uses crystalline structure in time and which can have potential for practical application. And we are working on this in Krakow. So currently we have following members: Shudong Tian, Veronika Bolec, and Ali and Mami. So that's all concerning crystalline structure in the resonantly driven system, crystalline structure in time in the resonantly driven system. And now I'm going to switch to another topic, which is crystalline structure in phase space crystals. Phase space crystals means Lindgren Guo. And in 2013, he realized that the band structure, energy band structure, can be created if the system is resonantly driven. And he was interested and he focused on the crystalline structure in phase space. And there is also a recent book by Lindgren on phase space crystals, which I warmly recommend. And this is Institute of Physics Publishing 2021. Okay, what we start? We start with a single particle, but not in the system which can reveal nonlinear resonances where period of the motion changes with energy, but we, we consider particle in a harmonic potential. So the frequency doesn't depend on the energy. And then, and you assume also that the harmonic oscillator is periodically driven. And then it turns out that in the system, we can observe the creation, emergence of the infinite crystalline structure in the phase space. So let us consider, there are many publications by the group of Ding and Guo, but let me describe the system which they consider in the publication. And this is 2018. And the precise exact references you can find in my book. What they consider harmonic oscillator. And the periodic driving here means that the system is periodically kicked. Maybe you remember that we consider periodically kicked by rotor. So when we have only particle, for example, on the ring, and which is perturbed periodically by the same kind of perturbation as we consider here. But now we consider harmonic oscillator. And the period in this unit, the period of the harmonic oscillator, of the particle in the harmonic oscillator is 2 pi, but we assume that the driving, so the period of the driving fulfills the resonant condition. So we have S21 resonance. And we are interested in the quantum description of this periodically kicked harmonic oscillator. So, and in the units we are using to write this Hamiltonian, the commutation relation between the position and the momentum operator is given by some effective Planck constant. And this effective Planck constant depends on the, in SI units, depends on the work of Planck constants, depends on the parameter K, I will explain in a moment, depends on the mass of the particle, and depends also on the frequency of the harmonic oscillator. This is the wave number because we kick this the system with the help of this potential, and this potential is actually some periodic potential in space, and the space periodicity is given by some by 2 pi over k. This is the wave number which I have in mind. And what is I would like to stress, because it will be very important, that looking at this effective Planck constants, we see that we can change the value of the effective Planck constants, because we can either change the frequency of the harmonic oscillator, but then of course we have to follow also, you know, the driving period has to follow this resonant condition, but we can also change the wave number. So I assume that we have a control over the effective Planck constant. And this is exact Hamiltonian, but now we are going to derive some effective Hamiltonian, and the procedure is similar as we applied in the description of the crystalline structure. That means that first of all, okay, we apply the so-called rotating wave approximation. In our case, when we had nonlinear resonances, we called it secular approximation. So the rotating wave approximation means that we switch to the moving frame. Moving frame means that we apply the unitary time-dependent unitary transformation, which is following one. This is a creation and annihilation operator. They correspond to the creation and annihilation of the excitation of the harmonic oscillator. So simply, if we have harmonic energy of the harmonic oscillator, then we can express this with the help of the creation and annihilation operators for the excitation. That means that we have Planck constants A double A plus. So that's the first step. That's the second step. In the moving frame, we neglect oscillating terms, or in other words, we average the Hamiltonian over time. And we obtain the following time-independent effective Hamiltonian. This is a strength of the kicking, K, that one. Here we have S, which is the resonant number. Then we have the sum over J, from J equal 1 to the resonant number S, cosine of X times cosine of 2 pi J over S, plus P times sine 2 pi J over S. Okay, so now we would like to analyze what the structure we can obtain from this Hamiltonian. And if it was the classical Hamiltonian, then it would be easy, because in the classical case, what we can do, we can plot in the phase space the contours for the constant energy, and then we will see how the phase space structure looks like. But if we switch to the quantum description, then we have a problem, because we have crystalline structure, but one dimension along X does not commute with another second dimension along P. It is usually when we have two-dimensional crystalline structure, then of course X and Y operators commute. No, there is no problem. So in order to represent quantum structure, we have to use different techniques. And one way is to calculate the average value of the effective Hamiltonian in the states which are called coherent states. Coherent states are mathematically, there are right eigenstates of the annihilation operator. This operator is not sufficient because there is difference between right and left eigenvectors. And these eigenvectors are, when we calculate the average value of the position operator such state, then the real part of the complex number alpha tells us what is the average position, and when we calculate the average value of the p operator, then imaginary part of this parameter alpha tells us what is the average momentum. This is average values, but of course we are interested what happens with the standard deviation variance of this operator in this state, and it turns out that these coherent states are optimal. The variance are the minimal possible from the Heisenberg uncertainty relation, and moreover, the uncertainty along x and y and x and p directions are the same, so they are balanced. In other words, this is an optimal way to represent phase space structure in the quantum case. Okay, so now we have the tool, we have the result, and let us look how different crystalline structure in the phase space look like depending on which resonant driving we choose. And it turns out that for S equal 4, we have a squared lattice, squared structure in the phase space. For S equal 3 or 6, we have the hexagonal structure. For S equal 5 or S greater than or equal 7, we have quasi-crystalline structure. And of course, this the best way is to show you the picture. Okay, so this is the average value of the effective Hamiltonian in the coherent states. This is, as I told you, P corresponds to the real values of the parameter alpha. Different real values correspond to different choice. P corresponds to the imaginary part of this complex parameter alpha, and the real part corresponds to the average position. And that the first one, it is for S equal 4. That one is for, this is a hexagonal structure, S equal 3. And this is for S equal 5. And now let me, so for S equal 4, we have the square structure, and this is the same plot as in left one, but in the 3D version. So we see how the energy, average energy of the particle changes when we change the position and the momentum. And what is important that if we consider classical particle, and we choose the energy, then we obtain the contours in the phase space correspond to the trajectories. So we see that we have minima and maxima, and we have if we choose different contours, that means that our particle can evolve around the minimum, but it also happens the same around maximum. If we choose a position here in the phase space as an initial point, then there is a trajectory around the maximum. So that is in the classical case. But when we switch to the quantum case, then I will consider the quantum case next time because we are running out of time. But in the quantum case, of course, as in the crystalline structure, we expect that the eigenstate of the system are delocalized along the entire crystalline structure. So we expect infinite crystalline behavior, so to say. Okay, so that's all for today. And we will see next week, and that will be the last lecture. And of course, people who are interested in the exam, I have prepared the list, so please sign up. That's all.